Okay, let's get started. Today, we're really diving into the geometry of area.
Yeah, but not just, calculating square feet.
Right, exactly. We're looking at these, well, sometimes surprising relationships between shapes, how their areas connect based on where they sit.
hmm Our source material calls them area propositions. Think of them as sort of fundamental rules.
Rules that show how position can make areas equal or related in simple ways. So the mission is basically to understand why these positional things matter so much for area.
Precisely. It's about getting beyond just area is the space inside to what happens to that space when figures share things, like a base, for instance.
Okay, and the source jumps right into this idea of equal figures, which sounds simple, but maybe isn't.
It's a key distinction, yeah. In this context, equal figures means figures with equal areas.
Ah, okay. Not necessarily identical shapes.
Not at all. That's the big point. Congruent figures, exact copies, always has equal areas,
Sure.
obviously. But figures with equal areas, they might look completely different. A long, skinny triangle could have the same area as a sort of squat one.
Got it. Equal area, not necessarily equal shape. So how do these relationships come about? The source talks about figures on the same base. What's that mean here?
It's pretty straightforward, actually.
Yeah.
Just means two shapes share a common side, like they're built on the same foundation line segment.
Okay, like two houses sharing a property line, almost.
Kind of, yeah. The source shows examples, maybe two four-sided shapes sharing side AB, or two triangles sharing side BC. That shared side is the base.
Makes sense. But then it adds another condition, which sounds more specific. Figures on the same base and between the same parallels.
Yes, and this is where the really interesting rules kick in. It's a tighter constraint.
So what does it add?
Well, they still need to share that common base.
Yeah.
But also, the vertices, the points opposite the base for both figures, must all lie on one single line. And that line has to be parallel to the base.
Okay, so they're sandwiched. Same floor, same ceiling height, basically.
Exactly. Grounded on the same base and capped by the same parallel line. The source shows like a parallelogram and a triangle sharing base AB. And their top points C, D, E are all on a line parallel to AB.
Right, I see the diagram. That parallel constraint is crucial then.
It absolutely is. It fixes the height, essentially, even if the shapes lean differently.
So what happens when shapes meet both conditions? Proposition 1 is about parallelograms.
Yeah, Proposition 1, it's powerful. Parallelograms on the same base and between the same parallels are equal in area.
Always.
Always. The example shows two parallelograms, maybe ABCD and ABEF, sharing base AB. Points D, C, E, F are all on a line parallel to AB. Even if one looks skewed, their areas are identical. You don't need angles or other side lengths, just that setup.
Wow, okay. Position is everything. And then Proposition 3 connects triangles and parallelograms.
It does. Another really fundamental one. The area of a triangle is half the area of a parallelogram if they're on the same base and between the same parallels.
Half. Exactly half.
Exactly half. Look at the figure with triangle ABE and parallelogram ABCD. Same base AB, same parallels AB, and some line through D and C. The triangle's area is precisely 50% of the parallelograms. It's a fixed ratio just from the position.
That's neat. And Proposition 4, just triangle.
Proposition 4 says triangles on the same base and between the same parallels are equal in area.
So not half of anything, just equal to each other.
Right. If you have two triangles, say ABC and DBC, sharing base BC, and point A and point D are on a line parallel to BC, their areas are the same. They share the same base and the same height, effectively.
Okay, so these rules must be why some examples look tricky but have simple answers. Like that trapezium example, number 4, where those two triangles inside it end up equal.
Exactly. That example uses Proposition 4. It takes two larger triangles, ADB and ACB, that share base AB and are between the parallels AB and DC, so their areas are equal.
Right.
Then you just subtract the area of the triangle where they overlap triangle AOB from both. What's left?
Triangle AOD on one side and BOC on the other.
And since you subtracted the same amount from equal areas, AOD and BOC must be equal in area too. The propositions make it logical.
That's pretty elegant. So wrapping this up, it seems these really basic geometric conditions, sharing a base, being stuck between parallel lines, they create these predictable, sometimes counterintuitive equalities or simple ratios in area.
Even for shapes that look nothing alike. It really drives home that equal area doesn't mean congruent. It's about the spatial setup.
It's dictated by the base and that parallel boundary.
Yeah.
Which brings us to a final thought for you, the listener. If simple rules about position, like same base and between the same parallels, can enforce these kinds of area relationships, what other seemingly basic geometric principles might be out there, linking properties of figures in ways we don't immediately expect?